converting our ketone to carboxylic acid esters. So the conversion is from ketone to carboxylic acid ester. This is an oxidation reaction, and we are using peroxy acid as an oxidizing agent for this reaction. So our peroxy acid is an oxidizing agent here, and it is being reduced to our carboxylic acid. So it's a redox reaction. One species is getting oxidized, other species is getting reduced. Let's take an example. We have cyclopenta pentanone. This is cyclopentanone. We are reacting it with an peroxy acid. It looks like a carboxylic acid, but if you see carefully, there are two oxygen atoms here. It's a peroxo bond, so this is called as peroxylic acid, and it is getting converted into a from 5-member ring to a 6-member ring, and this ring has incorporated an oxygen atom here, and our acid peroxy acid is being converted into carboxylic acid. So this is the conversion. This is a cyclic compound, cyclic ketone. If we take an aliphatic ketone, I have taken the simplest ketone here. If you react it with the peroxy acid, what is happening? Your oxygen atom is being incorporated between your methyl group and carboxylic carbonyl carbon. So we are getting this product. Alright. But if you have two different ligands on your ketone, or you can say if your ketone is unsymmetric. Here if you see, one side we have ethyl, other side we have methyl group. If we react it with the peroxy acid, there are two possibilities. There should be two products. One case when you get an oxygen incorporated on the side of ethyl group. Other one is when oxygen is attached to the methyl group. But only one product is formed majorly, that is with the ethyl. The reason is here an alkyl shift is occurring. If you see the first reaction, this methyl group is being shifted here as CH3 positive. So if you take the example of this one, there are two possibilities. Either your CH3 positive will shift, or your ethyl carbocation will shift. Now if you see which of these two will be most stable, ethyl carbocation is more stable. So the shift of the alkyl group, or you can say shift of the alpha carbon, that alpha carbon will be shifted, which will form a more stable carbocation. Alright, so that's why we are getting this product. I have written this in words. In case of unsymmetric ketone, out of the two possible alpha carbons, the one that stabilizes the positive charge more effectively will be shifted, or you can say the carbon, alpha carbon, which is more substituted. These two carbons are alpha carbons. This carbon have only hydrogen atoms, while this have a methyl group and two hydrogens. So this carbon is more highly substituted, so it will be shifted to the oxygen atom preferably. Alright, now we'll see the mechanism of the reaction. So we are taking a general reaction of acetone with our peroxy acid, and the products are formed like this. Now let's see how the mechanism works. We have acetic acid and our peroxy acid. This will attack on the proton, and you will get a positively charged protonated acetone. This could exist as this structure also, where carbon have a positive charge, and it will preferably exist like this because oxygen is more electronegative as compared to the carbon, and according to the rules of resonance, the atom which is more electropositive will have the positive charge. So this carbon is electropositive as compared to the oxygen, so that this carbon will have a positive charge. Now the remaining species, what is left of this compound? CH3CO, CH3COOO negative. So this is what is left here. Now what will happen? This species will attack on this carbon and form a compound like this. Now the methyl shift will occur. This CH3 positive will shift from this carbon to this oxygen, and this bond will be cleaved. This bond cleaves because the oxygen-oxygen bond is very easy to break. It doesn't require much energy to cleave this bond. So this bond will be broken and it will be eliminated as CH3COO negative, and the second part will be this. Now again resonance can occur here, so it can exist like this also and this also. Now what happens? This species will eliminate the proton. It can attack on this hydrogen, and the proton will be gone with this species and carboxylic acid will be formed. So it is eliminated like this, and you are left with the carboxylic acid ester. So this is the mechanism for this reaction.